Looks like we've got our usual suspects here today, so we can get started. I know at least one other couldn't make it. He had something come up that pulled him away at this time, but the rest of us are here and we'll have some fun. I know my idea of fun is different from many, but I do enjoy math and teaching it. So do you have any questions about anything we've talked about thus far before we jump into 5.4? All right, and let's go ahead and start with 5.4. And here we're talking about the properties of logarithms. And one of the things I like to do is just list them out to start. Rather than going through bit by bit and adding, I thought I'd just start with a list of the properties that we need to pay attention to. Now we saw a couple of them yesterday. If we have log base A of A, that will always equal 1. And we saw log base A of 1 is always 0. So we saw those, and that is true for natural logs as well, because natural log is a logarithm. It just has a very particular base. And we also saw the change of base rule. We've got log base n of m. Then we could convert that to log base b of m over log base b of n, where b can be anything we want. And we often make it a 10 because that's what our calculator button has. I don't know why I switched from all caps to mixed, but I'm sure we can follow that. All right, we've got a few other basic properties of logarithms that we will use in this section. These are actually in a box on page 352. So let me highlight that so we can refer back to that whenever we need to. We've got the product rule, and that states that log base b of mn is the same as log base b of m plus log base b of n. That's our product rule. We also have a quotient rule that says log base b of m over n is the same as log base b of m minus log base b of n. We will be using these. I just like to share them and then we'll start to practice them. So now we've got the power rule. It tells me log base b of m to the p equals p times log base b m. And notice all we did there was pull that power. It was up here on the argument and we just pulled it out in front. That's the power rule. And you can go the other direction too. If it's in front, you can put it up as a power inside. That can be very useful for simplifying logarithms. And so combining the power rule and the rule we had up at the start, if we've got log base a of a to the x, that just equals x. Power rule might bring the x out in front, and log base a of a is 1, So you end up with x times 1. So that makes sense using a couple of these other rules. They've just simplified that out for us. And correspondingly, we've got a, and it is raised to log base a of x. Notice the base of the exponent is the same as the base of the log within the exponent. This also equals x. So 10 raised to the log base 10 of 2 would be 2. And so those are the list of the properties that we are going to be working with in this section, section 5.4. And the rest of the section just has us practicing these properties. So let's go ahead and do that for a little bit. But I wanted to show you each of those. And then as we're going, I'll try to give the name of the property we're using. And I'll save this so that we can refer back to this whenever we need to. So often the problems in this section say express this logarithmic expression as a single log, or simplify this logarithm, or something like that. So let's take a look at some examples. If I have log base 5 of 5 times 125, I've got a couple of ways that I can look at this. But if I use the product rule, as a reminder, the product rule states that if I've got the log of a product, I can split that into the sum of the log of the first term times 2 plus the log of the second term. So let's do that. We don't necessarily have to, but it might make this easier. I probably don't even need a calculator if I split this. I can write this as log base 5 of 5 plus log base 5 of 125. Notice I had a product, and I just split this into the sum of logs. And when I say I had a product, it was a product within the argument of the logarithm. It wasn't 125 times log base 5 of 5. It was log base 5 of this product. Now that I have that split, log base 5 of 5 we saw from our properties yesterday, that's 1, because the base here, raised to what power, is the argument. 5 to what power is 5? That's 1. We'll do the same idea here. 5 raised to what power is 125? That's 3, because 5 cubed is 125. So this is 4. So log base 5 of 5 times 125 is 4. We could have done that product first and had log base 5 of 25, which is what you get when you multiply 5 by 125. And now we could ask ourselves, to what do you raise 5 to get 625? Well, that is 4. So that looks a little shorter. I didn't write it all out. Maybe I don't remember that 5 to the 4th power is 625. I could go to my calculator if I don't have the change of base on there. And I have to do the change of base rule. I could do log of 625 divided by log of 5. Plug that into my calculator, and I'll get the 4. And so there are several ways we can approach this exact same problem. The product rule, converting from a product, or the log of a product, to the sum of logs, made it pretty easy without a calculator. Multiplying the 5 by 125, we've got 625. Maybe not as easy to remember that 5 to the 4th is 625. We've still got the change of base rule, so we could use this, only now I have to grab my calculator. And what if I fat finger it or something and I don't get it typed in right? I'll get the wrong answer. So I like to make things as simple for myself as I can, and the product rule does a pretty good job of that with this problem. Let's try a different one. Say we've got log base t of m over 8. This one I won't be able to solve because of all these variables in here, but I could use the quotient rule. I've got the log of a quotient becomes the difference of logs. Log base t of the numerator minus log base t of the denominator. So that's a simple application of the quotient rule. Sometimes it gets a little trickier. We might get log base b of p squared q to the 5th over the 4th b to the 9th. And so this is rather extensive. And I can see we've got quotients, we've got products, and we've got powers. So let's see, I'm going to start with the quotient rule. Because I've got a quotient, that'll split this up. So I've got log base, that looks kind of weird, log base b of p squared q to the 5th. I'm going to put that in parentheses because it's still the log of that product minus the log base b of m to the 4th b to the 9th. And now I've got some product rule in here. So I could split this into log base b of p squared plus log base b of q to the 5th minus, I'm going to put this in parentheses so I don't forget to distribute that negative sign, log base b of m to the 4th plus log base b of b to the 9th. All right, rather extensive. So let me just kind of distribute this so it's plus a negative and a negative, just kind of distributing that sign through. Now we've got power rule. Power rule says I can bring each of these out in front. Well, this one was one of our properties. Anytime you have log base, we had log base a of a to the x was just x. So this one, I don't even have to do the power rule. I can just use that other property. But let's use power rule on these others. So we've got 2 log base b of p plus 5 log base b of q minus 4 log base b of m minus 9. And so we took this logarithm that was actually kind of simple in a complex way. What a weird thing to say. But we split it up into 3 individual logarithms and a constant. Now we could have done that just by looking at it. Notice, thinking power rule, this 2 is going to go out in front, and we'll have log base b of p. The 5 will go out in front, log base b of q. Anything in the denominator is subtracted. So we would have 4 minus 4 log base b of m, minus 9 log base b of b, and log base b of b is 1. And so sometimes you can just look at it and break it up that way, where anything in the denominator is subtracted and the things in the numerator are added. We could go the other direction. If we were given a sum like this, we could combine those together into a single logarithm. Now I know this is kind of weird. Why would you want to split it up like this? I think a good example goes back to that very first problem we had. You bring that back up where splitting this up into the sum of two logs made it so I could do the work in my head. And while having P, Q, M, and B here doesn't necessarily lend itself that way, if there were values in there for P, Q, M, and B, then splitting this up might very well make it much easier to do the calculation. And so I like to take the time to talk about this conceptually with the understanding that later there may be times where it will benefit us greatly to split this up, or even to combine things at a different time. So we'll want to consider that. Let's do one that's similar. And actually, I could probably just use more of the page here. Let's do log base b of x squared y over b cubed. This, and I'm going to just kind of speed this one up, kind of like I was talking about at the end there. Power is going to go out in front, and because this is in the numerator, it'll be positive. Power is 1, so even if we bring that out in front, it's not going to make a difference. Log base b of y, and then we'll subtract because the b cubed is in the denominator. Log base b of b cubed is just 3. So that's what we would get with this one if we split it up. We can do the same process I did before and start with the quotient. So maybe we would have log base b of x squared y minus log base b of b cubed. We could do the product rule here with the first term, log base b of x squared plus log base b of y minus, and we know this one from our earlier work, that that'll just be a 3. And then we would apply the power rule to this too, bring that out in front, and we will end up with that solution. So while I did jump to that fairly quickly, you can also see that following our earlier process will get us to the same place. Before I do any more, are there any questions on what we've done so far? All right. Let's get to a different type of problem. This one says, express as a single logarithm and if possible simplify. How about log of 0.01 plus log of 1,000? Now, product rule says I can combine these into a single logarithm because it's a sum of logs with the exact same base. And so this would become the log of 0.01 times 1,000, which is, let's see, 0.01 times 1,000, you move the decimal over twice, 10. 1% of 1,000 is 10, and the log of 10, recall if there's not a base written, it's a 10. 10 to what power is 10? That's a 1. Now we could have typed this into our calculator. Log of 0.01 plus the log of 1,000. We would have gotten that answer of 1. But by combining these together, if my calculator's batteries are broken or the screen is cracked or I forgot it, or batteries don't get broken, if the batteries are dead and the screen is cracked, then I can still do this kind of work. But I need to remember the power rule or the product rule to make that so. How about log of 10,000 minus the log of 100? Well, because I'm subtracting logs with the exact same base, I can combine those into a single logarithm that is the quotient of those two arguments. And dividing by 100, I can pretty well just cancel the zeros, and I end up with log of 100 and the unwritten but understood 10 raised to what power is 100? That's 2. Once again, I could have typed that into a calculator, but by using this property, I can fairly quickly realize that that difference of logarithms is as a result of 2. So it's not too bad. We simplified it into a single logarithm and simplified it even further down to a single integer, which is awful nice. I just heard a question or comment. Oh, no worries. Glad you made it. All right, we've been talking about the properties of logarithms, Phil. And the first thing I shared was the list of properties that is found on page 352 in the book. And now we're just practicing those. So different ways to play around with logarithms. So let's try one that's even a little differenter, more different, a little stranger perhaps. Natural log of x squared minus 4 minus the natural log of x plus 2. Okay, quotient rule, because I have the same base, quotient rule says I can combine those to the natural log of x squared minus 4 over x plus 2. Now I recognize I have the difference of two squares here. The first term is a perfect square and the second term is a perfect square, so I could factor that one into square root of the first term minus the square root of the second times the square root of the first term plus the square root of the second. All of this is still over x plus 2. And now that I have that, I can see that those two factors are identical. So I can cancel those because anytime x plus 2 is divided by x plus 2, we get 1. And this is simplified to the natural log of x minus 2. So while we had polynomials there, one was a quadratic and one was linear, the difference of those logarithms, because they had the same base, allowed us to use the quotient rule. Then we could factor and simplify and get this down to a single term. And now perhaps you can see even more application for this. We, for some reason, need to take logs of polynomials. We might be able to simplify this down. I seem to prefer working with linear terms as opposed to a quadratic. While I do have the quadratic formula and so on, linear terms are still easier for me to simplify. And so we'll into things like that from time to time. All right. Let's do another one sort of like this. Perhaps a little lengthier. Natural log of x minus 3 times the natural log of x minus 5 plus the natural log of x plus 5. That looks crazy, doesn't it? But if we break this down into things we know, just kind of get back to the basics, I think we'll be okay. If we see that right here, I've got sum of two logarithms with the same base, there I can use the product rule. Here I've got a term out in front that I could bring up using the power rule. And then here I've got a difference. So the difference of a logarithm with another one will allow me to use the quotient rule. So let's do those in the order I just mentioned. Let's see what we can get. So let me move the screen up a little bit. I don't need that other stuff up there, but I want some space. So first I'll apply the product rule. So we've got natural log of x is still there, still minus 3, but the product rule says I can take the natural log of the product of these two terms. X minus 5 times x plus 5. If I FOIL this, x squared minus 5 plus 5x, I'm sorry, minus 5x, so those will cancel. Minus 25, we've essentially got the difference of two squares. So x squared minus 25. So I've got that. There's our product rule in order. And as a matter of fact, I don't really even need these braces anymore because there's no difference inside. Now let's go ahead and apply the power rule. So I'll take this 3 and bring it up as a power in the argument. So we've got natural log of x minus the natural log of x squared minus 25 cubed. And now we'll apply the quotient rule because I have the difference of two logarithms. So that becomes the natural log of x over x squared minus 25 quantity cubed. So now we took this long logarithm and simplified it down to a single logarithm by using those three properties of logarithms. First the product rule, then the power rule, then the quotient rule. Simplified it down to a single logarithm. Now, I do want to point out some potential pitfalls that I don't want you to run into. But I see these mistakes too often. And that's why I bring them up. These are big no-nos. Don't do these. I just see it too often to ignore. I'll see somebody take the log of base b of mn, which product rule says that would be log base b of m plus the log base b of n, but for some reason they kind of distribute the log, and they do log base b of m times the log base b of n. They just multiply those two. Those aren't equal. Don't do that. Another one I see is log base b of m plus n. And again, they distribute the log. Log base b of m plus log base b of n. Those aren't equal. This thing on the right-hand side would be the product, m times n, not m plus n. So that doesn't fit with those properties. Oh, here's a good one. Log base b of m all to the p power does not equal p times log base b of m. The difference between what we've got here and our property was if the exponent is only on the argument, then the power rule exists. If it's a power of the logarithm, that power rule doesn't apply anymore. So be really careful. Do not do these things. I've seen it happen a lot. Just be careful with those. I'd hate to see you run into the same problem that some former students have. So sometimes I hesitate even showing that because I don't want you to have that stuck in your mind. So let me bring back these proper uses of the rules. Here we've got the exponent is on the argument, and so the power rule applies. Here we've got a log of a quotient becomes the difference of logs. The log of a product becomes the sum of logs, and vice versa. The sum of logs becomes the log of a product. The difference of logs becomes the log of a quotient. If you've got some coefficient to your logarithm, you can raise that coefficient up as an exponent to the argument. So feel free to use these rules both directions, but make sure you're following the rules as written, that we're not deviating from those, trying to apply algebra within a logarithm, because a logarithm itself is a process. It is a function. It's not something that lends itself as well to algebra within it. It's something you have to treat as a whole. It's essentially, it's a number. A logarithm is a number, and we want to make sure that we're not mistreating it. So let me give you another type of problem that I see often. They might tell us that we've got a few givens. They may say log base A of 2 is 0.301. And log base A of 7 is 0.845. And log base A of 11 is 1.041. So they give us very particular logarithm values. And then they'll ask us to find, say, log base A of 14. So if these things are true, then I can use those to find this, because 14 is 7 times 2. And I have the log of 7 and the log of 2. So now that I have the log of a product, I can split that into a sum using the product rule. I know log base A of 7, that's 0.845. I know the log base A of 2, that's 0.301. I add those two together, and I get 1.146, which would be the log base A of 14, if those first three are true. Now, the thing is, we don't know what base they're using with those givens. So just relying on a calculator doesn't necessarily work. Using these properties will work. And sometimes using a calculator will give you a rounded number. Say the A actually did equal 10, but it's rounded differently, so you plug it into your calculator and you miss it. I'm not saying the A is 10. I just take the numbers they give us and play with that, and then I'm covered. Let's try another one. How about log base A of 1/7? That's the same as log base a of 7 to the negative 1, right? With our exponent rules. I could use the power rule now. Bring this negative 1 out in front. So that would be negative log base a of 7. I know log base a of 7, 0.845. So using my power rule, and yes, we used an exponential rule first within the argument, we were able to get the answer there. Let me do another one that is similar, or a few more that are similar. So we've got some givens. Log base b of 2. And notice we didn't always use everything they gave us. We only used the ones that apply. Say log base b of 3 is 1.099, and log base b of 5 is 1.609. And then they want us to find some others. How about log base b of 125? We've used 125 a few times already. We know that's 5 cubed. Power rule says I can bring that 3 out in front. I know log base b of 5, 1.609, and that times 3 is 4.827. And now I know log base b of 125, just applying these properties. How about this one? This one's a little different. Log base b of 15b. Now that looks weird, but I think we can do it. We've got 2, 3, and 5 as the arguments up above in the given. I know that 15 is 5 times 3, and then we've got times b as our argument. So let's go ahead and use the product rule and split this into log base b of 5 plus log base b of 3 plus log base b of b. Well, what do I know? Log base b of 5 was given as 1.609. Log base b of 3 was given as 1.099. Log base b of b is 1. So this looks like, what, 3.708. Just adding those three numbers together. Even though we had this b in here, the fact that that is the same as the base of the logarithm gave us an option. But we wouldn't necessarily have had any other way. Not any variable will work out quite that nicely, but this one really did. How about log base b of 3 over b? I'll give you a few minutes and let you work on that one. And then I'll work it out as well and make sure we're all on the same page. I just realized that the clock I used to end class is 2 minutes fast. So we've been getting out about 2 minutes early, unless we go 2 minutes late. I don't suppose that hurts too many people's feelings, but I regularly had 2 more minutes than I thought we did. So I should pay more attention. I see a quotient within the logarithm, so maybe I'll use quotient rule, which is, that's a terrible G. Log base b of the numerator minus log base b of the denominator. I see 0.099 is a possible answer in the comments, so let's keep going. I think you're right. Oh, I can't hide the givens, otherwise I can't do the problem. All right. So log base b of 3 we know. That's 1.099. Log base b of b is 1, and that does indeed equal 0.099 as the answer. So we can break these down into bits and pieces. And I've put a problem like this on the exams in the past. I thought it was a good exercise to let you practice a variety of uh, logarithmic properties and think a little beyond what a basic problem might have. How can I get from these odd problems to something that will let me use the givens from the get-go? And I like that type of problem where we have to say, well, how do I get from here to there given these tools? I've seen so many wonderful, down-to-earth people solve so many problems in life, like a broken tractor, broken four-wheeler, something like that, just by thinking, what do I have? How do I get from here to there given what I've got? It's sometimes astounding what people will come up with, which is one of the reasons I like these. I like to see people push themselves and find ways to get from here to there using a very particular set of skills. Quote the movie. I do like movie quotes an awful lot. Okay, have we got any questions about how to solve these problems or anything to do with these properties of logarithms? Not seeing any? I think we might as well start the weekend a couple minutes early. We've covered the properties of logarithms. Those are, like I said at the start, on page 352 of the text. Make sure you do the homework. It looks like there are quite a few problems in there, 19 of them, that will let you practice these properties. You will simplify logarithms. You will combine and simplify. You'll use these various rules, just like we did here. So you'll take a big logarithm and split it into sums and differences, or you'll take sums and differences and combine them into a single one. You will do some like these last ones, where you're given particular logarithms and need to solve for another one. But in each case, we'll be using some of these properties. Perhaps not all of them, but at least some of them will show up. And some of them will show up again and again. It'll give you a chance to practice those. This is an important weekend, celebrating our independence. I hope you do so. And I hope you do so safely and that you have an outstanding weekend. Looks like the weather should be nice. Take care of yourselves, and I'll see you next week.
Thank you. Have a good weekend.
You're welcome.